Hi, it's Robin. A hobby of a lot of Commodore 64 users back in the day was collecting pokes that they would use to either change the behavior of their Commodore 64 or particular games. Listings of pokes would often end up in magazines, and people just like to collect them, try them, and it was a frequent topic in the computer magazines of the day. I've discussed some of them here before. All the poke command does is puts a certain value in a certain memory location in the computer's memory. Some of those are actually hardware registers, such as the video chip. If you poke 53280 and give it a number like 1, that represents the color white. You see the border color has changed to white. 0 is black. And the default is 14, which is light blue. But this might be the best poke I've ever encountered. Maybe the biggest bang for the buck is poke 788,82. And press return. And you might notice that it looks like the cursor has stopped flashing. Well, it has. You can still move around. But here's the interesting thing. If you use the cursor keys, it actually leaves a trail behind. That single poke has converted the Commodore 64 into an Etch-A-Sketch. Seems I always draw something rude whenever I got one of these. And what's really interesting is you can still change the color. So if I hold down Control, I can change it to, say, purple. Control 4 is cyan, another bluey green. Control 6 is green. Control 8, yellow. And even the other 8 colors from the Commodore key are available. So that kind of orange, brown, light red, gray, and so on. Pretty neat. And even the clear screen function still works, so you just want to shake your Etch-A-Sketch. Just hold down Shift and clear, and the screen clears. Oh, occasionally it glitches like that. Let's try that again. There we go. Once in a while you get a little trail left over, or a little dot left on the screen. So I find that really cool. It's a funny thing. This might be like the 5th or 6th video now I've accidentally made about Etch-A-Sketch type things. One of the first programs I ever typed in my life was on my Timex Sinclair 1000. And it was a little Etch-A-Sketch program. I've made a video about that at least once. And then the equivalent program on the TI-99. And then there was even that little Etch-A-Sketch program hidden in the cassette J card of a blank data cassette tape, which I typed in a while ago. These things just keep popping up. But who knew that there was one just lurking here inside the C64 all along, just one poke away. Again, that's poke 788,82. Okay, neat that you can just type in the middle of it too. Even more versatile. So I was curious about the story behind this, like who discovered this and why does this even work? The earliest occurrence of this poke that I found was published in Commodore User Magazine, the June 1986 issue, on page 88. In the section in the bottom right corner entitled One Poke Draw. Probably one of the shortest pieces of magic yet. It uses just one poke, yes, one, to provide you with a dinky little drawing program. And here it is, poke 788,80. Notice that's slightly different than the poke I've given. and we'll get into that in a little bit. When you've typed it in direct mode, just use the cursor keys to draw. Better still, you can change color easily by using the Control and the CBM key with numbers 1 through 8. John Palmer of Devon. So I don't know if John Palmer came up with this himself or what, or if he found it out from somebody else. That's the earliest occurrence I've found. And then probably more popularly, it showed up just a few months later in the September 1986 issue of Zap 64 on page 9 in the letter titled Humming Noise. And here Alan Weir of Wood Lane, Liverpool, even confesses that he bought a copy of Commodore User magazine. Back then, you're supposed to be very loyal to your favorite magazine, so you shouldn't be buying one and writing to another. And he says, I have also stumbled on a useful poke for drawing on the screen. Just type poke 788,80 and use the cursor keys. I just found it interesting to find a second example, but it was just copying from one magazine and writing it into another. I have stumbled on it by reading the other magazine. So how and why does this poke work? Well, I'll just reset the computer here. Now, I don't know if that poke 788 sounds familiar. Another popular poke back in the day was also poke 788, but instead put the value 52 in it. At first, it doesn't seem to do anything, but it actually has two side effects. If you print the time clock, see, it's 23 seconds since we rebooted the computer. Well, it's still 23 seconds since I restarted the computer. This poke actually stops the time clock from running on the C64. And it also has another side effect. If we make a program that just does something like print hi in endless loop, hi, normally we press the stop key and we would break the program, stop it from running. But that is not working. Well, that's the other thing that poke does. Fortunately, you can still hold down stop and tap restore, and it'll still break out of the program that way. And actually, that will undo that poke. So now if we run it, I can press stop, and it actually does stop the program. Okay, so both of those pokes are in the same memory location. I'm just going to use my Kung Fu Flash here. I've got it programmed with Adrian Gonzalez's Snappy ROM version 5.31, which is an unofficial upgrade to the Super Snapshot. And here in BASIC, we'll freeze the machine and go into the Super Snapshot monitor. Okay, well, what is this memory location? Put the hash sign, which means convert in this monitor. Plus means a decimal number, 788, that's the memory location we're poking. In hexadecimal, that is 0314. That might be a bit more familiar to some of you who have done some machine language programming. It's actually the interrupt vector, the IRQ vector for the C64 when the kernel is active. And if we look at the contents of 314, normally it points to, in low byte, high byte format, EA31. This is the main kernel interrupt handler, which does things like read the keyboard, update the time clock, flash the cursor, which are all things that we've seen affected by these pokes to 788. So basically, when you poke 788, you're modifying this memory location right here, hex 314, which is the low byte of this 16-bit address. EA31 is the default. Normally it is 31 hex, which is 49 decimal. When we modify it to 52 or 82, then what we're really doing is redirecting the interrupt to a different part of the kernel ROM a little later in memory. Okay, so like I was saying, the normal default is EA31. So let's look at that code. So it starts off with a jump to subroutine of FFEA. That is actually the subroutine that updates the Jiffy Clock and checks the stop key. So you can see right here why when we poked 52 in, right here, decimal 52, that changed the address to 34, EA34, the next line after. So that poke, 788,52, that disables the stop key, just makes the kernel interrupt, instead of executing this code, it begins on this line, jumping over this kernel routine. So that's all it's doing, is you're changing where the interrupt vector points just slightly, and it can have a big effect. Of course, if you poke the wrong number in there, you'll probably just crash the computer. Disassemble FFEA. All it does is it's a jump to another address here, F6, 9B. We've actually looked at this code in previous videos where these 3 bytes, A0, A1, and A2, are a 24-bit time counter. And if you remember, here's the little bug where this 24-bit value is actually 1/60th of a second bigger than it should be. And that causes a very, very tiny inaccuracy in the Jiffy counter. So it seems a little bit strange that Commodore wrapped these 2 routines in. All the preliminary code is updating that time clock, that Jiffy clock, and then down here, where it checks with memory location DC01, which is the CIA, the input-output chip that reads the keyboard. And right here is the code for actually checking the stop key after the Jiffy Clock update. So that's why those 2 functions are tied together. If you want to disable the stop key, you also end up inadvertently stopping the Jiffy Clock. Okay, that was just an aside. Back to EA31. Okay, so here's a chunk of the code. After the call to stop, it messes around with these 0-page locations CC and CD. Those are actually cursor control. So I'll show some disassembly from the super excellent pagetable.com C64 disassembly by Michael Steele. This is an amazing resource, and I'll include a link in the video description. So these are flags that control the cursor, if it's blinking or not, and if it's time to blink. So for the Etch-A-Sketch program, obviously we want to skip this. Actually, let's just calculate that right now. When we poke the 82 in, oh, sorry about that. I meant to put plus 82 decimal. Okay, and that gives 5252 hex, which is to right here. So we're skipping from here all the way down to here. So what does this code do? Well, this blinks the cursor right here. And if it did blink, this resets the time, the number of jiffies. This D3 stores the cursor position. And here's another kind of flag or toggle that checks if the current cursor is the original character or if it's the flashing cursor. You see, there's no hardware support for that flashing cursor. It's all just emulated or simulated through the reverse characters. Like even the cursor we're looking at right now, it looks like it's blinking. Well, it is, but all it's doing is either it has a regular C or a reversed C, which are both in the same character set with the high bit set. There's 128 regular characters and then 128 reversed characters. They're just the inverse, where each 0 pixel becomes a 1 and each 1 pixel becomes a 0, just the inverse. So that's all that's happening, is this character is being modified. And there are these various counters to keep track of the time of that, and also what character was originally there, because you need to restore it when you move the cursor away. And this keeps track of the color of the cursor position, because of course you can actually change the cursor color here. And it has to remember what the original was, but also what color you have the cursor now. So all this involves keeping track of the cursor and both the character's shape and the color, and making sure that blinks properly and allows it to restore it after. So that's why the Etch-A-Sketch works. is basically we're just jumping over all the cursor code, and it's jumping right ahead to the part that actually just plots the cursor, so it's always stuck on and never flashes off. And that's just by saying the interrupt vector, instead of executing any of this code, it just jumps right ahead to this point here, skipping all the blinking cursor part. But there's still a discrepancy where I'm saying it should be 788,82, but the magazines are saying 788,80. Well, if we look at what 80 is, that's hex 50. Let's disassemble again from EA31 to EA50. We'll notice that there is no instruction starting at EA50. It actually starts at EA4F. EA50 would be this byte here. That's weird. Why would it jump mid-instruction? That could cause a crash, or at least, or quite possibly have some kind of negative effect. Well, if we disassemble at EA50, we'll see that quite amazingly, it's going to interpret the 24EA, which is actually just the address. The jump to subroutine should be to EA24, which apparently is a routine to calculate the pointer into color RAM, but instead it's going to treat this 16-bit address, EA24, as an opcode 24 with parameter EA, which just so happens to just be a bit command. Well, the bit command is kind of famous for being, not very well used 6502 instruction, and also fairly harmless. All it does is does a number of tests from the accumulator against this memory location, EA, and sets some status registers, like if it's set to 0, if it's equal, or so on, but otherwise it makes no changes. As long as you are not relying on any status registers after that, such as equality or negative, that's the minus bit, which appears the code here does not. The load A is going to change those status flags anyway. Was I saying registers earlier? I meant status flags or status bits. The status register has several flags in it that are used for doing branches. Whether if something's equal, it can branch if equal, branch if not equal, branch if plus, branch if minus, and so on. Poking 788,80 causes the interrupt vector to start here, but it's just a very harmless bit command, as it turns out, and then it continues executing at load A F3, which is at EA52, which is why I'm suggesting. So really, it isn't a big deal, but it seems very strange to me that the popular poke, 80, would be jumping 2 bytes earlier, and if anything, just wasting a couple cycles here. So I'd say that poking 82 is better, but it doesn't really matter. That is a very funny coincidence, though. It does make me wonder, though, when John Palmer or whoever first figured this out, were they just randomly poking around and it happened to work? I would have thought that they would have looked at the kernel disassembly here and, strategically chosen the bytes that they wanted, but instead, no. It appears that they just lucked into it, unless there's something I'm missing. Okay, so that's why that works. What does happen if you poke step 82? Let's poke 84 just to go one more instruction later. Oh, even that seems to work. So I just poked it ahead to this 54 even, where we're not even loading it. Well, that's nice that it's so redundant it can handle a whole bunch of pokes. Okay, so whatever poke you choose, maybe this is the best poke ever. Do you know of any better? Leave a comment and let me know. And if it's even more interesting, I'll make a video about it. Okay, thanks very much to my patrons for their support. Thank you for watching, and we'll talk to you next time.